All right, so let's actually put this to the test. You ready? Now, I'm going to do the integral. I think you guys will like this. I'm going to do the integral from 1 to 9 of 1 over x squared dx. Now, I realize that we know how to take this integral, okay? But it'll make our lives simpler just because the derivatives, remember when we do all this error-bound stuff, it'll make our lives simpler. Now, to be able to deal with a function that we know how to take the derivative of. Or excuse me, and we know its behavior. So here's what I'm going to do. I'm going to approximate the value of the integral by I'm going to do m sub 8, I'm going to do t sub 8, and I'm going to do s sub 8. And I'm just going to show you how to set these up. Then we'll grab my calculator, we'll throw them through, and we'll see what we get. All right, so let's go easy. First things first, I want to find delta x. All right, so delta x, I made this gentle on you, as you can probably tell. This is always b minus a over n, which in this case is 9 minus 1 over 8. So delta x is 1. Phew, thank God. Now, it's not a bad idea to think about what this function looks like. This function looks, 1 over x squared looks like this, doesn't it? So what we're doing is, we're starting here at 1, and then we're going to finish way out here at 9. And I know that my delta x is going to equal 1. All right, that's terribly drawn. I apologize for that. But let's take our time with this thing. All right, so we know that m sub 8 is going to be delta x times all of the midpoints, right? So delta x is 1, right? Now, what's the midpoint between 1 and 2? How do I know the next value over is 2? Because delta x is 1, right? So 1 plus half of 1 is going to be 3 halves. So this is going to be f of 3 halves. That's going to be the height of the rectangle, right? If I grab that guy right there, that is a little bit small, but you get the point at this point, right? Now this is where it gets easy. Plus, I'm going to add 1 to it. I'm going to remember to get over to the next rectangle. We did these before. I simply add the width of the subinterval, which is 1. So I don't think of it as 1 because I'm adding fractions. So I think of it as 2 halves. So this is going to be f of, what would we say, 5 halves plus f of 7 halves plus f of 9 halves plus f of 11 halves plus f of 13 halves. Now, when do I stop? Well, when I've taken 1, 2, 3, 4, 5, 6, I got to do 2 more, right? Because I got to get to, I need 8 total rectangles being built. I'm going to go plus f of 15 halves plus, plus f of 17 halves. Now look at this last one. 17 halves is 8.5, which, sweet, if this is 9, then 8.5 is going to be the midpoint between 8 and 9. All right, that's it. There's nothing to it. Okay, and then we're going to throw that in our calculator, and we're going to get it here in just a sec. But let's write up the other ones first. Try and write up t sub 8. See what it looks like. All right, just give it a shot. In other words, like all this goes into our calculator, so we're not afraid. But try and actually write up what t sub 8 is before you plug it in your calculator. So just give it a shot, and meet me back here in a sec. All right, so delta x is 1. Right? I remember the formula. Remember, if I stumble back here, where's my t guy? Let's see, my t guy is right here. This guy right here is my t formula, right? So I start at the leftmost endpoint, and then I just do a bunch of 2's, and then I finish at my rightmost endpoint. So I take delta x, which is 1, and I divide it by 2, because remember, that's what the formula said. Let me prove that to you. The formula says delta x over 2. So my delta x in this case was 1, which made it really simple because I'm simple. And I divided by 2, so off I go. And then I'm going to do this. I'm going to go 1 times f of 1, because that's my leftmost endpoint, plus 2f of 2, plus 3f of 3, whoops, 3f of 3, excuse me, plus 2f of 3, plus 2f of 4, plus 2f of 5, plus 2f of 6, plus 2f of 7, right? And then plus f of 8. Whoops, sorry, plus 2f of 8, and then plus f of 9. That's my other endpoint for trapezoids. So remember, that f of 1 plus f of 2 is the area of the first trapezoid. F of 2 plus f of 3 is the area of the second trapezoid, etc., etc. That's where these coefficients of 2 come from. All right? Let's do S sub 8. All right, so remember, let's look at our formula. It's back here. It's not nicely written, but you're going to have to bear with me. Look at this guy. Here is my Simpson's approximation. So I got delta x divided by 3, and then remember it goes 1, 4, 2, 4, 2, 4, 2, 4, all the way until I get to the 1 again. Excuse me. So S sub 8 is equal to delta x, which is 1, divided by 3. And then all I'm going to do is f of 1 plus 4, f of 2 plus 2, f of 3 plus 4, f of 4 plus 2, f of 5 plus 4, f of 6 plus 2, f of 7 plus 4, f of 8 as opposed to f of a, plus f of 9, right? And that's it. Throw in your calculator. All right, now let's do a little cooking show thing here. But remember, it's an idiot box. It's only as smart as the idiot pushing the buttons. So right now, throw this thing in your calculator and see what you get. I'll throw it in my calculator, and I'll meet you back here, and we'll check to see who got what, okay? All right, see you in a second. Okay, so let's see how everybody did. Oops, so let me show you. All right, from my midpoint, I got 0.8238. Now, I may be a little off on that, but I double-checked it, but I could have been crazy. The thing to remember with this is that f of 3 halves is 1 over 3 halves squared. You know what I mean? So it's 1.5 squared. This is going to be 2.5, 3.5, 4.5, 5.5, et cetera, squared, right? And then each one of these is just 1 over 1 squared, 1 over 2 squared, 1 over 3 squares, et cetera, et cetera. So I got, from my M8, I got this one was approximately equal to 0.823, well, let's just call it 0.824. For my T8, I ended up with this one was approximately equal to, this one was a little ugly, 1.034 is what I got. Now, why are these two so different? Well, you got to remember, when I build trapezoids on this guy, because it's decreasing in concave down, my trapezoids are going to way over approximate, right? They're going to be above, like if I do that on a bigger scale, if I've got a value here and a value here, my trapezoid is going to pick up all this extra area right in there every single time, right? I'm going to end up with extra area every single time. So that's why I have such an over approximation. And then for my Simpsons, I ended up with approximately 0.926. Now, I may have been wrong. It's an idiot box, and I'm quite the idiot, so I could have screwed that up. But enough about that. Now, here's what I'd like to do is I'd like to walk you guys through how to use these error bounds, because I know that they can be a little tricky. So let's do the error bound for the trapezoid first, okay? So whoops, sorry about that. So what do we have to do? I'm going to make this big so we can see more of it. All right? What do we got to do? The first thing we got to do is we got to figure out what B and A are. That's easy enough. I got 12 as a freebie. I know what N is. It was 8, right? We had 8 subintervals. And then I got to figure out what this K thing is. So let's stumble over here. I know that K has got to be greater than or equal to. So first things first, we're going to figure out the error bound for the trapezoid. Whoops, absolute value. I know that it's going to be less than or equal to K times B, times B minus A. I'm getting ahead of myself. Cubed over 12 times N squared. Remember, when you're dealing with formulas and you're old like me, always double check your work, right? All right, there we go. Now let's deal with this K thing, because I know that's probably the most daunting part of the whole thing. What the heck is the K? Well, I know that K has got to be some value that is greater than or equal to the absolute value of the second derivative of x. Well, okay, let's not be afraid. Remember, this is on the closed interval from A to B. True? So I know f of x is equal to what? Well, it's our integrand, right? I know that f of x is equal to 1 over x squared, which you may be thinking of this as x to the negative 2. So f primed of x is going to be negative 2x, excuse me, to the negative 3. F double primed of x is going to be 6x to the negative 4. Now think about what this looks like. This is 6 over x to the 4th. Well, what does 6 over x to the 4th look like? What does this function look like? Well, it looks a whole lot like 1 over x squared, only it goes, oh, bam, it gets really close to 0 really quickly. But if this is 1 and this is 9, and this function right here is f double primed of x, and I need to find a value that is greater than or equal to all of the values of the second derivative from 1 to 9. Well, where is that? It's right here. Now I got lucky because this function is what we refer to as a monotonic function. It decreases throughout. So I get to grab a value at the end point because that's the biggest value. I know that f double primed of 1 is biggest, right? It's the largest value on the closed interval from 1 to 9. True? So I'm just going to let k, this implies, ooh, my work here is a little nasty. This implies that k is going to equal 6, which happens also to equal f double prime at 1. Again, I grabbed 6 because 6 is the biggest value that f double prime of x reaches. It happens to reach that at the left endpoint. So now it's a no-brainer. All I got to do is plug and chug. I know that the error bound for the trapezoidal approximation when n equals 8, we should probably label some stuff, right? I know that a equals 1, b equals 9, n equals 8, and k equals 6. And then I just plug and chug. Absolute e of t is going to be less than or equal to 6 times, now what do we got? We got 9 minus 1 cubed divided by 12 times what? 8 squared. True? So this is going to be less than or equal to 6 times 8 cubed divided by 12 times 8 squared, right? And this is equal to, you can tell, 8 squared goes away, I get that. This is 48/12, affectionately known as 4. All right? That's cool. I mean, it's a little bit nasty because think about this. What this says is that my error that I can expect from this trapezoidal approximation, that means that the actual integral may be as big as 5, approximately 5, or as small, quote unquote, as -3. All right? I can be off by that much. Now, we'll show you what the actual integral is here in a sec. All right? Now, let's go back to this formula real quick. Let's go back to this guy. Let's do the midpoint. Notice that k isn't going to change because it uses this same parameter. K has got to be greater than or equal to the second derivative, right? So let's go back over here. We're going to figure out E sub n. Absolute E sub n, which is just, well, I shouldn't say E, it's error of the midpoint, right? Which we know our approximation was 0.824 in my crappy handwriting. It's less than or equal to 6 times 9 minus 1 cubed divided by, now what was the denominator? It wasn't 12, it was, you just look at it and you, like I remember that it's twice as big. Sometimes I remember and sometimes I don't. So this is going to be 24 times 8 squared, right? So this is going to be less than or equal to 6 times 8 cubed divided by 24 times 8 squared. Same algebraic trick. 48 divided by 24 is 2. Now you may be asking yourself, whoa, Ripley, these errors are huge. Why are they so big? Why are they so big? Can you answer that question? That's a really important question. And the answer should be relatively obvious. The interval from 1 to 9 is a relatively big interval, right? If I'm integrating from 1 to 9, that's a relatively big swath of the function. And look at my delta x. It's 1. I'm only taking 8 subintervals. That's a pretty clunky approximation, isn't it? You know what I mean? If I want to get a heck of a lot more accurate, I'm going to let n get bigger. And if you think about that with these formulas, if n gets bigger, then this denominator gets bigger. And as the denominator grows, the size of these